All right. So the section 1.4, I just realized I didn't take off the keyboard for this thing, so there it is. This section 1.4 has to do with continuity and one-sided limits. So continuity of functions and one-sided limits to functions, okay? So continuity, or to be continuous, means to be unbroken, right? So we can kind of look at like three little quick drawings here. Actually, let me do these in black, but so there's one there, another one there, and just one more. Okay, let me just put some arrows here so at least we know this is a coordinate plane. We're not going to make any tick marks on it. Now, there's three different types of functions I want to draw. There's going to be one right here. We'll call this f of x, and we'll put c right there. Then we'll draw a different one here that looks kind of similar. We'll call this g of x. Okay, and then we'll draw one more. Oh, and by the way, I forgot to put on the second one. This is C right here. This will be C for this graph. So let's just take a look at these three different types of graphs. So we're just going to observe something, okay? First off, you should observe that f of c for the first graph here, f of c is defined. Okay, in other words, it has an answer. The answer for f of c is right about here. Okay, and if you wanted to find that answer, it would be right there. Okay, that would be our f of c, right? So f of c is defined, and you'll also notice that f of x is continuous. There are no gaps or anything like that. Okay, so f of x is continuous. Now, if you look at the blue graph, we can see that g of c is g of c defined? Like, does it actually have an answer, g of c? Actually, it does. It may be disconnected, but g of c is right there. It's not the open dot, it's the closed dot, right? So g of c is defined. Don't know the answer because we didn't mark anything, but it's just g of c. It does have an answer. And g of x, though, is not continuous, right? It breaks. So g of x is discontinuous. Now, I forgot to put h for this one. Sorry, this is h of x. Is h of c defined? Yes, it is, right? It's down here. This would be h of c. So h of c is defined. Is it continuous, h of x? No, right? H of x is discontinuous. Now, I'm just kind of curious. Does f of x have a limit at c? I'm going to put a real quick question. Does f of x, or you know what, let me do it this way. Does the limit as x approaches c of f of x exist? And I'm going to ask the same questions for g of x and h of x. Does the limit as x goes to c of g of x exist? And the third one, does the limit as x approaches c of h of x exist? So we'll take the first one. We'll do the first one first, right? Does the limit as x approaches c of f of x exist? So is there a limit? No? How many of you guys, just by showing hands here, how many of you guys say, no, it does not? 2, 3, okay. How many of you guys think it does? Okay, a lot more. And some of you guys just aren't sure. The answer is yes, it does. Okay, yes, it does. How do I know? Well, let's zoom in. If I draw a line coming in from the left-hand side to that point, and then one from the right-hand side to that point, does it look like they're going to crash? Yes, so that means the limit does exist, right? Limit does exist. What about for g of x? How many of you guys think, yes, it does have a limit? How many of you guys think, no, it doesn't have a limit? All right, so nobody said yes. The rest of you guys said no, and then the others were still unsure. So if we draw the left side and the right side coming in, does it look like they're going to crash? No, so there is no limit, right? So, and then right now I'll write the answer for them, but let's look at h of x. Yes or no? Yeses, raise your hand. 1. No's, raise your hand. So a little bit more no's, but not too many more. Now that you see it, let's see. Is there a limit? Well, we come in. Does it look like they're going to crash? Yes. Is there a value there? No, but do limits really care if the answer actually exists, since they're theoretical? No, right? So does the limit exist? Yes. The limit would be here. The actual answer would be there. For like an actual concrete answer, h of c, that's the point on the bottom. But the limit is where the empty dot is. Okay? So remember, limits do not need to have a concrete answer. They are theoretically trying to reach a specific place. And even if there's a point there or not, it doesn't matter. They can still take that value, even though there's a gap there. Okay? So let me go back and just kind of write the answers to these things. So we asked, does the f of x exist? Yes, this one does. Does g of x exist? No. H of x, this would be a yes. Okay? So how do we prove whether or not something exists? Well, we got to make sure that it's continuous, right? A lot of times whenever we're trying to show that a function has a derivative or a limit in certain places, we check for continuity. So how can we check for continuity? I'm about to give you guys a definition that you must memorize. Okay? Maybe one day I quiz you and tell you, give me the definition of continuity. And you're going to have to write it down word for word. Okay? So please make sure you guys know this. So definition of continuity. At a point. So if I ever want to check, is a function continuous at a point? How do I do that? Well, it takes 3 steps. Okay, but let's just write down the prerequisites first. So it says a function f is continuous at C if the following are all true. So number one, f of C must exist. Okay, so you got to be able to find an actual value for it. So like f of 2 equals 7 or something like that, okay? So f of C must exist. Number two, the limit as x approaches C of f of x must exist. So not only must it have an actual answer, but it has to also have a limit at that point. Okay? And step 3, basically step 1 has to equal to step 2. So the limit as x goes to C of f of x must be f of C. So step 1 has to be equal to step 2. Okay? So step 1 has to equal to step 2. So just to show you an example of this, let's go up to g of x. Okay? So does g of c exist? Yes, right? Does the limit exist at c? We said no, right? So this is not continuous at c because part 2 failed. Let's look at h. Does h of c exist? Yes. Does the limit as x approaches c for h of x exist? Yeah. Are they both the same value? No. This one has a value here for the limit. This one has a value here for the actual answer. They're not the same. So is there continuity at c? No. All right, so then how the heck do I prove continuity? Well, let's look at f. Does f of c exist? Does the limit as x goes to c of f of x exist? Yes. Are they both the same value? Yes, they're both here. So therefore, I have continuity at that point. Okay? So that's how that definition works. Okay? Yes, you will see that every once in a while on an AP exam. They'll ask you to prove continuity. They'll say, prove to me that this thing is continuous at this point. So you literally have to use those 3 steps, right? Show that it exists, show that the limit exists, and show that the existent value and the limit value are identical. Okay? So, all right. Now, let's talk about something called removable discontinuity. Like, can you fix it? So I always tell people, it's kind of like, you guys have seen the little cartoons or the story of like a little boy or maybe even a cartoon character is walking by a dam and it notices there's a leak. So what do? Remember, there's a cartoon. They see water coming out of a little hole. What do in the cartoon? Well, they plug it up using what? Well, usually they use their finger first, right? Because it's silly. So it's a cartoon, right? There's actually a story about that. But they'll plug it up by putting their finger in the hole, right? And then another one pops up, then they plug the other finger, and then they plug their whole hand, and et cetera, right? So this is kind of like the idea of removable discontinuity. There's going to be a hole, and we just got to plug it up, okay? So Let me show you an example of removable discontinuity. Okay, we're going to fix this really quick. So example number 1. Let's try to fix the discontinuity of this function, okay? So we know that this is not continuous where? Where is it not continuous? At 4, right? Because that would make the bottom equal to 0, so we have discontinuity, right? So this is not continuous at 4. Now if I were to graph this, just to see it, there's just a little sketch, okay? My scale's by 2. So if I were to graph this, my actual graph would look like this. Let me see. Well, I don't want to do that. Let me simplify. F of x is equal to x minus 4, x plus 4 over x minus 4. So I have cancellation. Remember, x cannot equal to 4, right? We can't have that. So that means f of x is equal to x plus 4 as long as x doesn't equal to 4. So this is a linear function. Okay? This function is linear. So starting at 4, it's going to kind of look like this. Okay? It's going to look like that. Go ahead. What? The limit can't... Okay, you figured out what... Okay. So, all right, I just graphed the function. It looks like it's supposed to be some kind of rational expression, but it's not. It's just a linear function with a hole, right? I want to make it continuous, but you see a hole there, right? So what I'm going to do is do what the little cartoons do, right? I'm just going to stick my finger right there, and I'm going to plug it up, right? What if I were to plug that up, what would be the y value for it? 8. So this is what I'm going to do. If possible, I can rewrite a function and make it have removable discontinuity. Okay, so as long as x does not equal to 4, it can be that function. Okay, but if x equals to 4, we said it has to be 8. So there you go. And all I did right now was I just plugged up the hole, right? I just put a little thing right there, and there you go. I filled it. Okay? You can't always do this, though. Okay, I'll give you an example of when you can't do this. But I was able to do it here. It was pretty easy. I could see it. I'm like, oh, look, it's just one hole, so I'll plug that up. No problem. Okay? So let's go to example 2. What if I give you g of x equal to 1 over x, where x cannot be equal to what? 0, right? X cannot be equal to 0. So let's graph this one. So again, example 1 is called removable discontinuity. Okay? Example 2 is called non-removable discontinuity. Okay? But we'll give it that title in a bit. Okay, so here we go. Now you guys should obviously know that there is an asymptote here, right? So it can't touch that section right there. Where's the hole for this graph? It's the whole y-axis, right? Well, I can't just use one finger to cover that up. I mean, I can't use 10 fingers to cover that up, right? I can't use an infinite amount of fingers to cover that up. It's the whole thing. It's impossible, right? The hole can't be like, you can't say like, well, I'm just going to make a hole like a really long oval, right? You can't do that, okay? It just has to be a point. There's no way I can just put one point. I can't just say like, oh, I'm just going to put a hole right there. That's perfect. That's exactly where it crosses. Like, no, you can't do that. So you can't fix this one. Okay? No way. So this is called non-removable discontinuity. Okay, you can't fix it. You can fix the other one, but you can't fix the one that I just showed you. All right. Any questions on any of this so far? All right. So the existence of a limit, okay, depends on the existence of one-sided limits. Okay. So there is a big old definition for the existence of limits, but we're not going to go through it. I'll give you the meat and potatoes instead of the whole buffet. All right. So existence of a limit says a limit exists for a function if the left hand, or I guess some people say left side, but I usually say left hand, and right hand limits exist, and very important, they both have the same answer. Okay? Now there is notation for left hand and right hand, or left side, right side. Yeah. So there is notation for left hand, right hand, or left side, right side. The reason why we call them left hand and right hand, if you guys look back here, because usually you're supposed to use your left hand, well, for you it looks like my right, but your left hand and your right hand to kind of trace a graph and then see if they crash. So they call them left and right hand limits, okay? But if you're not, using your hands, you could just call them left side, right side, just use your eyes, whatever. But both have to collide, right? They have to have the same exact limit. That's why I tell you guys before, we've kind of already talked about this, they need to crash. If they don't crash, there's no limit, right? Why? Because the left and right hand limits won't be the same. And if they're not the same, then the existence of a limit, well, it's not there, right? Because definition says left and right hand limits must exist. So you got to find both. And they both have to have the same answer. Okay? So let me write down the notation for this so you can see. I'm just going to say if the limit as x goes to c minus, if you see minus, that means left, okay, of f of x equals to L, and the limit as x goes to c plus, that means from the right side. Okay, so minus is left, plus is right, of f of x equals L. So notice both limits exist, both limits are the same. Then the limit as x goes to c, some people like to call it the whole limit because it's composed of both, right? The whole limit as x goes to c of f of x is also L. Okay, so if the left side limit is L and the right side limit is L, then the whole limit is also L. Now, sometimes limits don't exist for both sides. Okay, an example of this is coming up. Find the limit as x goes to 0 from the right of radical x. I got to see if I can make this a consistent size for this graph, but here we go. Okay, so the square root of x looks like this. So I said add 0, so let me put a little dot right here. They said from the right side. Well, I can do that. I can approach from the right. What is the height of that function as I approach from the right-hand side? 0, right? So the limit as x approaches 0 from the right side of radical x is 0. What's the limit as x approaches 0 from the left? Is there a left? No, right? It would be somewhere right here, right? We're looking for it from that side. But there is no graph to the left of 0. There's no graph. So that would be undefined. So does the whole limit exist at x going to 0? No, because we have two different answers. Do one-sided limits exist? Yeah, the right side. They don't both have to exist. Left and right hand don't always have to exist, but there is usually always the existence of one of the two. Okay? So just kind of like a little thing for you guys to know. Now let me see. I'm just checking something. So you guys already know these properties. So I think we're pretty close to being done. So here we go. Real quick theorem, sorry. But we're not going to call it a theorem. But let me write this down for you guys. Let me make sure I have this page lined up right. Okay, here we go. So polynomials rationals, radicals, and trig functions are continuous at every point. And you might say, well, wait a minute, Mr. V, that's not right. Okay, I know some functions that are rationals that are not continuous at every point, you might say, like we just did 1 over x. That's not continuous. But you're telling me that's a rational function and it's continuous at every point? Well, let me finish, right? At every point, here's the key, in its domain. Okay, so in other words, for 1 over x, is the value x equals 0 part of its domain? So 1 over x, right, this graph right here, is x equal to 0 part of its domain? No, you can't use it. Can I use any other number for it, though? And is it continuous everywhere other than at 0? Yeah. So my statement that I made, that every polynomial, trig function, rational, radical function, is always continuous, and then, little asterisks there within its domain, right? Now, why do we say that? Because if you get a polynomial function and multiply it times a trig function, those are two continuous functions, right? So if you multiply two things that are continuous, you continue to have continuity. They don't lose their continuity. Okay? So whenever you're given some problems and they ask you like, hey, do these things stay continuous, yes or no? Well, it kind of depends on the graph. You got to look at the graph and ask yourself, okay, do these things stay continuous everywhere? And if there's certain issues, then we have to say, no or yes. So let me give you an example of what I'm talking about. So here we go. Are the following continuous? Are the following continuous? Number one, we'll say, here's a function. And number two, we'll do g of x equal to just checking time here. We get out at 2:07, right? Still got 15 minutes. So I might try to push the rest of this in. It's just one more idea, but I don't know if we'll get to the last example. If we don't, we can finish it tomorrow, but I'll at least try to get the next theorem in. What do you guys think? Example 4, part 1, continuous or not? I mean, is x a continuous function? Yeah. Is sine of x a continuous function? So if I add them together, should I get continuity? Yes. Right? So this would be yes. Question 2. Is 1 over x a continuous function? All right. So you might say, wait a minute, Mr. B, you said it was. I said at every point within its domain, right? So it is continuous everywhere at its domain, but in general, is 1 over x considered a continuous function? No. Is tangent of x considered a continuous function? It's actually not. You guys remember the graph for tangent? It goes like this. And there's like a bunch of breaks, right? Actually, I think I just drew cotangent. But there's a ton of breaks right there, right? So, yeah, for this would be a no. It's not. Both of these are not continuous. So they're not going to magically become continuous by dividing two discontinuous functions. Okay? All right, so last idea. This is one that you guys have to really understand the idea of this function. I'm going to write out the definition, and then we'll draw a picture to maybe help you. And if I have time, I'll do one example. If I don't, we'll do the example tomorrow. And I may give you the homework tonight, later on throughout the day, just so if you want to get started, you can. Or if you want to wait till tomorrow, that's fine too. Okay, that's up to you. But here we go. It's called the intermediate value theorem. The intermediate value theorem. We call it the IVT for short. Now I'm going to write this out exactly the way it's written in the book, because these are one of those things that you have to memorize. Because sometimes in the AP exam, they'll say, given the following is continuous and it exists at one point, what can I make an assumption from this information? Well, you might say, oh, well, intermediate value theorem will tell you the following. And you got to recite the rest of the theorem. Okay? Maybe not recite it, but write it down. So you got to know it. So just like continuity at a point, I say make sure you guys know that, the 3 steps, right? Make sure you have those down. Intermediate value theorem is something you should memorize, okay? So it says if f is continuous on the closed interval, on the closed interval a to b, and k is any number. This is all going to sound really weird, but trust me, once we draw it, I think it'll make a lot of sense. And k is any number between f of a and f of b, then there exists at least one number c in the closed interval from a to b, such that f of c is equal to k. Now there can be more than just one number c, but at least one number c. Okay, so go ahead and take a little bit of time, write that down. So if f is continuous on the closed interval from a to b, and k is any number between f of a and f of b, then there exists at least one number c in the closed interval from a to b, such that f of c is equal to k. And again, I will draw something for you guys so you can see. Now, usually this is used to prove the existence of zeros. Like, this function has a 0 at this point. This function has a 0 at this point. So this is what it's used for, okay? To prove the existence of a 0. So let me try to give you a picture that will kind of give us that idea here, okay? So let's see. All right, so we're going to start with our function f right here. There's our function f. And it says if f is continuous, okay, I drew a picture, a continuous function, on a closed interval from a to b, that means I got to close this off. So let's say a is here and b is there. Okay, so far so good. I've done the very first line of that definition. If f is continuous on the closed interval from a to b, it says, and k is any number between f of a and f of b. Well, first I got to figure out where is f of a and where is f of b. So f of a would be right here, f of a. F of b would be right there. So they said k can be any number, but it has to be between a and b. Okay? So I'll pick, let's just pick it right here. So far, am I meeting all the requirements of my theorem? Yeah, k is in between a to b. There's a continuous function that's continuous between closed interval from a to b. Okay, so everything is good so far. Says, then there exists at least one number c in that closed interval such that f of c is equal to k. Well, I got to figure out where that c value is. But they said f of c has to equal to k, so that means this must have come from the graph itself. And there you go. There's a picture of this theorem. They're saying you can find an x value that can give you any y value between f of a and f of b. Okay, I'm sure you're like, well, that's great. I drew a picture. I still don't understand what the heck you're doing, right? So let me put this in another way. And the example is usually a good one, but let me at least, we'll do the example tomorrow. We'll stop right now. But let me at least explain something to you guys. The reason why this theorem is used is to show that zeros exist. In other words, to show that the graph crosses the x-axis. How can I do that? Well, if f of a is a positive number and f of b is a negative number, right? And the graph is continuous, does the graph have to cross the x-axis in order to connect these 2 points? Right? So if I have something like this, let's say I have a point here and a point there, and it's been told to you that the function is continuous. That means these points have to connect, right? So did they touch the x-axis? Yeah. What if the graph looked more like this? Did it touch the x-axis? Yeah, multiple times, right? 1, 2, 3 times. Is it continuous? Yeah, it is. Right? As long as the function is continuous, it must connect those 2 dots. And in order for those 2 dots to be connected, it has to go from here to here, doing whatever the heck it wants to do. But at some point, it's going to touch the x-axis. At least how many times? At least once. Okay, at least one time. That's why this right here. It could be more than one, but at least once. So the example I was going to show you, which we'll do tomorrow, gives you a function, it gives you a closed interval, and what you have to do is prove that the function's continuous, or at least say like, hey, this is this type of function, so I know it's continuous, and then show them that one of the values is positive and one is negative, and if that's the case, then it has to cross the x-axis in order for them to touch. Right? In order to connect them, they have to cross the x-axis. Okay? So we'll do that tomorrow. We'll stop right now. Okay? So homework may come later on, or maybe we'll give it to you tomorrow, but we're pretty much done with this lesson.